All right. Okay. So what we have for you today is the continuation from last time. All right. We were talking about the heat. All right. And I think the key message for you guys was heat is energy transferred. All right. So there is some movement going on over there. And actually that was the key stuff about the dynamics. That's what we were talking about. So what we are going to try to do, like a simple stuff today, is starting talking about the heat and the direction of flow and how to use the equations that describe the heat capacity, right? So the ability for a substance or an object to store energy in itself. And we're just talking about the ability to store. If the storage of that thermal energy is big, we say that that substance has a high heat capacity. That sounds good, right? So if something that doesn't have a lot of room for it to store energies, then it has a small heat capacity. All right, that was the one. And then we were comparing between sand and water at the beach during the daytime. And then you guys sort of like, okay, match with the experience saying that, oh, okay, the water is not that hot, but the sand seems to be hotter in temperature. So that means the sand must have lower heat capacity. All right, that makes sense. All right, and we just found out, we found out last time that actually water is a huge heat capacity stuff, right? So it's a high heat capacity material. Okay, so what we're going to try to use that understanding is in the topic of something we call it a calorimetry. So this one is about the study of the heat that is flowing mainly in, well, back in the day, there was water, talking about water, why the water is getting hotter, why it can vaporize, why it can get like solidify, turns into an ice and everything. So that was a calorimetry. All right. So the key of this thing is just like, is using this to measure the specific heat of stuff. That's why we sort of like use this as a process of learning. All right. So here's the key. So what we are doing is this. So usually what we have in the study is you have two things and then you put them in thermal contact. Okay. So there must be something like in this slide over here, there might be like some temperature X. So let's call it, this is like T sub X right there. And then there is some sort of like some known mass or some temperature, but we don't have to worry about that. We just say, hey, we have another object have different temperature. All right. And if we assume, according to this assumption, that if the temperature of the right object is larger, or actually smaller, sorry, it's smaller than the temperature of the left-handed object over there, then that means there is a flow. That will be energy flow, or that's a heat flowing from hot to cold. Cool, that's easy. So what we're gonna do is we wanna evaluate this amount of heat, the amount of energy flow. Okay, however, because this, all right, let me talk like physics-ish a little bit. So when we talk about system, usually that means you have to pretty much pay attention to the boundary of the system, correct? So that means in general, what we have in general, what usually it means system, it means what are you actually paying attention to, and you don't care about everything else. So what I'm having right now is I'm just looking at these two objects right here. That is my total system right here. Everything else beyond this, I say I don't care at this point, or the setup probably assume that there's nothing else here. This is like the only two objects in the universe somehow. All right. So this is your system that you are talking about. So that means whatever happens is going to happen between these two objects. Okay. And because we say, hey, there must be some energy flow, or that's what we named heat. So if there is a heat flow in here, the amount of heat that is flowing out from one must be the same exactly the heat that actually entered the other. There's nothing else. All right. So what we can name about this flowing of the heat over here is we say, hey, there is a heat flow. We use Q for that. And let's say we can say there is a Q cold and a Q hot. Okay. When you say Q cold, mean it's in the colder object. So because it's colder, it means the heat will flow into it. Okay, that makes sense. but the amount of the heat that is flowing, the amount must be equal to the amount of heat that actually coming out from the hotter object. Everyone agree with this? All right, but my point is this. The point that I want to make right now is there is one is flowing out and there's one that is flowing in. So there is a sense of direction, even though this is not the direction that you saw in vectors, but there is a direction in and out. So there must be some, sign and stuff that's saying that, hey, there must be some, one is out. I mean, one is losing heat and the other one is receiving heat. So to phrase properly, I have to say, I will have to start with the magnitude or the amount of the heat flow. You guys with me so far? Hey, is that the sound is good? Is that everything is clear and nice? I don't know. Is there's no like breaking? Okay, yes. Okay, thank you. All right, so what we have over here is it's just saying that I'm saying that the amounts, right? I said amounts. But if you want to incorporate the direction to it, how would you do it? All right, so we must have some convention over here. So convention that we're going to use is this. So whatever system that you are talking about, if you throw in the heat, when you throw in the heat, I would say that is the positive heat flow. So it means sort of like we pay attention to the system. And if something is enter the system, so the system receiving something, so it's supposed to be like a positive change. Does that make sense? And if the system expands, I mean, sort of spend some energy or, there's some heat flowing out, we call it the negative direction. So that means in general, the heat must have the sign in the front to signify the direction of the flow. Okay, it's good. All right, there is a question comes in, why energy should eventually reach the equilibrium. All right, I'll explain that after I explain the calorimetry calculations. Okay, that's a very good question actually. Okay, so over here, so when we would like to take that into account, so zoom it in again. So what we call this one, I'm calling this Q hot, right? Because that's the heat that's flowing out from the hot object and it is flowing into the colder part. So for the Q hot, it's flowing out, but the Q cold is flowing in. If we would like to sort of attach the sign to it, and I want to make them equal in magnitude or the amount, I have to re-express this equation in this form. Q cold must be the negative of Q hot. You guys understand this equation now? All right, just to make sure that you know what I am talking about. Okay, the reason I need the negative sign in the front because just the Q alone, it has the sign attached to it all the time. Okay, positive heat means the heat flow into the system. Negative numbers of that means the heat is flowing out of the system. To make them equal in magnitude, I just need an extra negative sign in the front. And that is mathematically interpretation is exactly the same as what it means by absolute sign. You guys with me now? All right. So if you want to find the absolute of -3, what is it? Is a negative of the -3. That's what it is. So it's a mathematical expression actually. Okay. So actually, you have two ways to sort of like put this into an equation. If you prefer the like a original form, you must have a negative sign in the front. But if you say about Ajahn, it's just so simple. It's just one in and one out. I mean, why don't you just compare the magnitude or the amount of heat flow? Yeah, I agree. So if you just want to take that, you just care about the magnitude and you just say, hey, bring me just the amount and just equate them. So use either equation. These two works exactly the same. But I will explain in detail when we face the example. All right, what's the difference and what is kind of like a pitfall that you might like made mistakes if you don't care about the sign, or if you don't care about the sign, but then you treat it like having a sign built in and other stuff. You forgot about the absolute sign. I mean, things will go crazy. Okay. I definitely don't want my body. Oh no, you don't want. No. That will happen when you don't have any heartbeat anymore. No, that's not good. All right, but that's a good that's a good gig right there. All right, but to answer your question about why, so you're probably like wondering like why Dan? Why do we need like to reach eventually equilibrium? Let's zoom it in. And this is what happening in mechanics in the microscopic world. So when you have a hotter object, the T hot is on the left, but we already understand what does it mean by hot or higher temperature. It means it has higher kinetic energy. Make sense? So that means whatever in this left object, it must be moving faster on average. So if you think about gas, then just think about gas. So the gas molecule go crazy in here, traveling, blah, 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 on and on. But it's going to be fast in relative to the speed on the left. I use a smaller arrow right here. Okay. Now, that's what happened at the boundary. On the boundary, you have the left moving particle, the one on the left, or let me stick with the blue. So that means on the left, there will be one molecule that actually moves so fast. But then it's knocking with another one that actually moving slowly. You see what I'm saying over here? So now you can go back to momentum and you can talk about the energy transfer during collision and everything. That's what happens. So in general, when you say equilibrium, it means because every time that you put things into contact, there are some interactions all the time. And when there are some interactions, that means there's automatically some transfer of things. And where does that transfer goes until there's no more transfer? When the two sides must be exactly the same on average. You see what I'm saying here? All right, so as long as the left side of the object has on average the microscopic molecules moving faster than the right side, there must be some transfer from left to right. Okay, because the left is so like energetic at that point. So eventually the right hand side would get something out of it. But to make things like stop doing whatever you do, it means left and right must have exactly the same amount of energy. Okay, so that's the reason why heat flow from hot to cold. That, I mean, you cannot defy it. That's what it is. Because in a microscopic level, that's just like mini molecules is exchanging energy. Okay, makes sense? All right. That's good. Okay, so if that's good, then
Okay.
all right. If you guys, I hope you guys are okay. All right, then. So let's move on to the actual calculation. So we're going to combine the stuff that we learned about the heat capacity, and then we combine that with the calorimetry. But now you know that calorimetry is just something that there is a heat exchange, the heat flow, and then you want to use that to determine something about those part of the system. All right, let's start with this first. You have 500 grams of ice is added to an insulated cup containing 200 grams of water at 50 degrees Celsius. What is the final temperature? That's a simple question, actually. It happens all the time around you. You dump an ice into a bucket of water. You have a coffee, a hot coffee. You let it cool down. You say, hey, it's not cool fast enough. You want to dump an ice into it. I don't know. You guys do that sometimes, maybe. All right. So let's set that up. So in a realistic picture, it looks like you have a cup of water, 200 grams. So let me put some information in there. 50 degrees Celsius. Very good. And then you want to dump ice into it. And it's information is 500 grams. Of course, ice, because it's not like super like deep freeze ice or anything. So we assume it's always at 0 degrees Celsius. Okay, cool. All right. Now in the diagram, this is actually two things in thermal context. You guys with me? Yes. One is water at 50 degrees Celsius. The other one is ice at 0 degrees Celsius. That's perfect. That's already calorimetry. The setup is good. Okay. All right. So I hope you see what it's trying to do. Okay. Now, what is happening is, of course, the heat will flow from water to ice. So the ice will getting hotter. First, of course, it has to melt, right? Because you come in a solid water. So first, the heat that entered the ice will melt the ice. And then once all the ice has already melted, then the temperature of that melted ice will start to rise to the final temperature. Look at the water at 50 degrees C. Once it's removed some heat from it, then the temperature of the water itself will start to lower. Okay. Solid water. Yes, sorry. But that makes sense, all right? Solid water. Okay. Anyway, so what we have over here is what you're saying is, okay, we can say, let's assume that the final temperature to be X then degrees Celsius. All right. So that is our goal. Assuming that when this system reach the equilibrium, that temperature at the equilibrium point is X degrees Celsius. Okay, that's perfect. All right, so let's do it. So you have two sides of the story. So what I'm going to show you how it's done, and I hope by just doing this one single example, I think it will clear up everything about calorimetry. Yeah, I hope. I hope that efficiency is high enough. All right. Okay, so let's start with this. So I'm going to do a traditional way. I'm going to do everything without the absolute sign. So that means I'm going to show you that there is a heat flow out from the water. Okay. How much heat is flowing out from the water, guys? How much heat is flowing out? Okay, if I say how much, that means usually you can think in your head like you have an absolute sign, right? How much? Because I don't care about the direction. So I'll put that. So I'm going to show you the contrast between the two. All right, so let's do that. How much? How much heat flowing out? Because the water is the hotter part. So let me call that Q hot. And I just want to know the amount. It's going to be M, the mass of water. Let me put the subscript W in there. The C of water and the delta T, right? Here's the kicker. The delta T is right here. So if you only care about the absolute sign, this must give, you will have to set the delta T to be only the positive one. So let me put the absolute sign right here. That's good. But then you say, well, Ajahn, I don't want to deal with the absolute sign, just purely the heat flow. The formula will work itself out automatically. So I'll show you what it means by these two lines. Okay, first, the final temperature is X. The initial temperature is 50. All right, so what I'm saying is the mass of the water is 200 grams. So I can turn this into 0.2 kilogram of water. Specific heat of water, you can go back and look at the table. Yeah, if you want, let's substitute the numbers in here. So the specific heat of water is right here. So let's take the number of about, let's say approximately 4,200. Why not? All right, approximately. I think this is good enough. So I'm just going to plug that numbers in here. 4,200. And the unit is going, I can put the unit in there. It's going to be joule per kilogram Celsius, on and on. That is fine. Here comes the delta T. What should be the delta T? We emphasize every time that when you dealing with the delta T, it's a final minus initial all the time, because delta is the change. So the final temperature is X, initial temperature is 50. Yeah, all right, there's a question about the units. All right, that's good. Do we have to always convert into kilogram and the specific heat until? You don't need to if you know the value of the specific heat in gram and everything else. Yeah, I just saw it. You saw what? Saw what? Saw what? Saw what? What did you just say? Oh, okay. Talk about this 42. Okay, joule per kilogram. Okay, so some of you, maybe from chemistry and biology, actually, they know that C of water is 1 calorie, right, per gram Celsius. if you know the value in different units, yeah, that's fine. You feel free to use it. You can use gram and you can use calorie in your units. That is fine, perfectly fine. Okay, that's answer your question. Yeah, but what we are doing right now is I am sticking with the SI system. Okay, come back to our business over here. Everyone will automatically can tell that X minus 50 will give you a negative number because the final temperature is always lower than 50 for sure, because you dump some ice into it. So you see what I'm saying now? So if you don't have to deal with absolute sign, you don't have to worry about the amount, the magnitude and everything. The mathematics of the formula will take care of the sign itself, because that's the formula it's saying. See, these numbers, if at the end X is lower than 50, this whole expression will give you a negative number. And when you have a negative number, it means the Q hot is negative. And when you say a Q hot negative, mean the heat is flowing out from the hot portion of the system. Does that make sense to you guys? All right, so let me do one more time. Okay, let's talk about Q cold. If you talk about the amount of the Q cold, the thing in your head, you say, okay, Ajahn, let's take the mass of the ice. Take the C of the ice. But wait, but Ajahn, you have to go through the process of melting first. So you got it now? So the way that you can use those expression is before you can get to MC delta T, you have to get the melting process done. So you have to get the mass multiplied by the latent heat of fusion or solidification first. That you can look it up in the table again. Once you complete this process, and Mi times L sub F, that is the amount of heat that you need to melt all the ice. Once it's done, you are ended up with the water at 0 degrees Celsius. Then you follow up by warming that up. The delta T. Let me put in the cold part right there. Okay, you guys with me now? Okay, very good. So over here, then because when you look at this one, this is automatically going to be positive because you start from 0 all the way to X. There's no negative numbers in here. So absolute value of this one is fine. But if you say, but I don't want to deal with the absolute sign, I'm just going to start with the expression of that. ML and Q equal to MC delta T. So I'm not trying to do anything acrobatic. I'm just plug it into the original definition of everything. So the heat that enter the cold part, which is the ice, first will equal to the amount that need to melt the ice plus the mass of the ice when it's already in water phase, in a liquid phase. And then delta T, final temperature of ice is X. Initial temperature of this portion of the process is 0. You guys with me now? And as you can see, this portion right here is automatically positive. In contrast to the one on the top is automatically negative. And now you can see if I want to equate these two parts, because you guys know the magnitude must be the same. The Q hot and the Q cold must be equal in magnitude. So you can pair this with this, that is the magnitude equal. But to do this, you need an absolute sign in the front. I'm sorry, for the delta T. Or alternatively, of course, you can match this too. So you just say Q hot must be Q cold, and then you just put a negative sign in either side of this equation. Does that clear? But at the end, you get the exact same equation to solve, but depends on what you like. Some of you guys doesn't want to deal with the negative sign. So you sort of like tend to think of the amount automatically because you kind of know like, hey, what is the temperature change from here to there to here? And then you know exactly what should happen to it. So you only pick the positive numbers to calculate. Okay, but if you want to stick with the expression or definition right from the start, and then you want to stick with the definition of the delta, which is final minus initial, then you need to put a negative sign into it. But no matter what you do, at the end, you end up with the same equation that you need to solve. Okay. Okay. All right. Cool. All right. And that's it, guys. That's pretty much the only comments that I want to do. And this is the reason this is important because, of course, if you switch the x and 50 and the x, of course, the answer will be totally different. That's important. All right, let's come back here. So what we can do next is just to solve this. Okay, just solve it. So let's move this one out. All right, so you just equate these two equations, and then I think you're done. So let me call this equation number 1. You can call this equation number 2. And then you just say minus of the equation 1 equal to 2. Or you can say absolute of the equation 1 equal to absolute of equation 2. And then you're done. Once you solve for x, that is your final temperature. Cool. All right. I mean, numerical calculation, you guys can do it. Okay, here's the kicker of this problems right here. I really want you guys to go back and really look into the detail of the calculation right here. The reason is because there's something funny about this. And you can feel it. The reason that you can feel it because you look at this. But อาจารย์ you have water only like 200 grams. เอาน้ำมา2 ขีด All right. And then you dump like half a kilogram of ice into it. What are you going to end up with? Well, อาจารย์ I don't think it's gonna warm things up. I mean, I don't know. I mean, who knows? It's water at 50 degrees C. Maybe, maybe not. However, how can you tell that can you melt all the ice using just that 200 grams of water at 50 degrees C? The answer will be once again in the mathematics. If you really go back and try this, the x that you will get, I think, I'm pretty sure, you get a negative number out of this. Okay, let me highlight this one more. It's a negative temperature. It's a negative number. Let me put it here. So that means this equation is false. When I say false means, that means it traces back to your original assumption is false. Because you assume that your final temperature is somewhere above 0 degrees Celsius. When you have that assumption, you already put an assumption that the ice has to completely melt. However, if your mathematics, right, after numerical calculation, give you the negative final temperature, and that's going to be conflict with your assumption, that means that is an indicator saying that your final temperature must be still 0 degrees Celsius. That means that sort of get back to the question that, hey, ice still there. The 200 grams of water at 50 degrees Celsius can only partially melt the ice. All right, so don't forget to try this. I think this is a very good question, and then give you like a single one and then can practice everything about this topic of calorimetry.
Okay.
Cool. All right, then. All right, try it out. Next, we have a couple more exercise for you to try. All right, I got negative 24.4. Isn't that way too low? Yeah, that's exactly my point. So when you say negative 24.4, you have to, I mean, actually it's done. You say that, oh, okay, your final temperature is actually 0 degrees Celsius. You cannot dump the ice into a water and then bring it below 0, right? That's not possible. So that means your assumption that the final temperature is somewhere above 0 is incorrect. And then, I mean, but that negative number is not into waste or anything. It's still very useful. And it's an indicator saying that your final temperature is actually 0 degree and only some portion of ice is melted. Yeah, that's good. Very good. Thank you for that number. I'll take your word for it. Negative 24.4. I don't know. I'm not good with the calculators. Okay. All right. Try again, guys. Thank you for that number. Okay. Don't forget to try this. All right. Keep going. All right. Try again one more time. This is another good questions. And I think the question in the exam will be either, I mean, of course, mixing the two stuff. There's nothing else we can do. Or put one hot with the cold stuff, put them in contact, find the final temperature, and that's it. Or it might be a little bit more acrobatic, but it's very good to calculate and try this. Okay, everyone try this. It's really good. It's really good. All right. Okay, let's read through this problem together first. Okay, you have a 3-gram lead bullet at 300 degrees Celsius and is fired at a speed of 240 meters per second into a large block of ice. So you have like a huge block of ice waiting. Okay, let's do blue for that. There we go. All right, and there's a lead bullet. Travel 240 meters per second. And then you start to see that, oh, there is some velocity built into this. Ah, that must be something nice. Okay, 3-gram, 30 degrees Celsius bullets traveling 240 meters per second and stuck it is embedded. So it means once it's shot into this block of ice, it's stuck in there. The question's asking how much ice melts. And we assume that because it's a large block of ice, so that means the ice stay icy. You still have some ice left. So everyone knows the system on the right stay constant in temperature at 0 degrees Celsius, right? You're not completely melted ice. Very good. Very nice. Okay. Kinetic energy plus temperature. Oh, but wait. Not the temperature though. Because the temperature has a unit of Kelvin or Celsius, right? And the energy is in a unit of joule, right? That expression is not good. Okay, your friend just put it in the chat that there is a kinetic energy plus temperature, but it's almost there. I know what you're thinking. Is the kinetic energy is another form of energy that need to get transferred to the block of ice. I'm pretty sure that the block would shatter. Maybe not. Maybe not. I don't know. Yeah. Think about the movie. It might be Hollywood hoax or anything. Yeah. I don't know. Haven't tried one. How can we try it, right? We don't have gun and stuff like that's violent stuff. Okay. Correct. Very good. So the key point of this one, just to emphasize before we move on to other subjects, is that no matter what kind of energy, when it gets transferred, it can be determined as heat. And in this case, you not only comes with some form of temperature change, because of course the lead bullet starts at 30 degrees Celsius, right? But at the end, you guys see that the lead bullet has to cool down to 0 degrees Celsius. So there is some heat coming out from the lead bullet due to the thermal energy. That's one thing. All right. But the second thing is the bullet also carry with it the kinetic energy that's from the 140 meters per second. And eventually you stop. I mean, the velocity or the speed of the bullet at the end is 0. Let me put like some final V sub F. So that part of energy disappear as well. So where does it go? There's nowhere else to go except the ice that actually make thermal contact with it. Okay, guys? Okay, all right. So what I want to do is this. So now here's the whole picture over here. If I want to draw this in a diagram mode. So let's use different color here. So in the diagram, it will go like this. So on the left, that's the bullet. Oh, okay. All right. And on the right, that's, let me put a bigger one there. That's the ice. Okay. So first of all, the bullet start from 30 degrees Celsius. Okay. And then eventually at the end, it will start up like down to 0 degrees Celsius. So what I'm going to write down is this. So ice stay constant at 0 degrees Celsius. So let's look at the hot part of the system. The hot part of the system is the bullet over here. That's a Q hot. Okay, you guys with me? Okay, first, the Q hot is from MC delta T. The bullet cool down from 30 to 0. So it's the mass of the bullet. Let me put subscript B for that. C of the bullet, that's the lead. So let me put C of the lead there. And the change in temperature, it goes from 30 to 0. So final temperature minus initial. You guys with me? It's automatically negative. Everyone knows this because heat's leaving the bullet. But then because the bullet also carries 1/2 mv squared, that is its own kinetic energy. So I still have 1/2 the mass of the bullet and the speed of the bullet square. But then you guys also know that this energy actually dissipates to the block of ice. When you say dissipate, mean it's being released out. So that's also a negative direction. So you guys understand what the direction of the heat means now? When the heat is negative, mean the heat flow out of the system that you are considering. If the heat is positive, mean you're receiving the heat into the system. All right, now you turn our attention to the block of ice. It's a Q cold part. Okay, so that's the Q cold. So the part that the ice receive the energy is pretty much all of the things that eventually going to come from the Q hot. But what does it do to that energy? Melts the ice. So that's the M times L. And if you assume that the ice around this one is going to melt a little bit, so let me call like the X amount of the ice melts. So that will be X times L. Cool. And now all you need to do is just equate these two equations. And then you have two choices to do. You can just put an absolute sign to them and then just equate them. Or you can just take negative of one of these and then equate them. So let me do it one more time just to clearly find everything. So, I mean, traditionally, I would do this. Q hot with the negative sign will be equal to Q cold, which is the same thing as doing the absolute thing. And I would say is the M, B, C lead. Now I put a negative sign to it. It's going to be 30 plus 1/2 mass of the bullet, speed of the bullet initially, square, equal to the amount of ice melts times the latent heat of fusion and all this stuff. And from here, you can solve for X. Okay. All right. So that's done. And I hope by showing you these two examples, it's clear about the sign usage. How can you use the sign correctly? It's give you the idea of the direction of the flow. But for those of you that still don't like this kind of thing, if you look at the last equation right here, that's kind of makes sense because on the left is the amount of energy. This is how much energy that's leaving the lead bullets. This is the amount of energy that the bullet carries with it initially, and it's going to transfer to the block of ice. And once you get these two sum up, it will be equal to the energy that required to melt X kilogram of ice. Yeah, so if you talk in terms of the amount or just the magnitude, this equation also makes sense. But at least now you can make connection with the original equation if you like. I mean, the reason I spend so much time talking about the directions of the flow, the negative sign and all that stuff, because this is going to be quite important in a little bit later when we learn thermodynamics. Right? Sign is very crucial. You can make a wrong interpretation when you have opposite sign assigned to any quantity in thermodynamics. Okay, here there's some question comes in. Breaking the bullet will cause increase in heat. Yeah, correctly. So the reason that ice melts is just because, I mean, you have to, I mean, there is energy required to stop the moving bullets. And that's why it turns into heat, right? So when you put like a bullet west and then you get shot. So if you saw in some movie, you have to actually have to really take it out quickly because it's actually is hot. Part of it is, I mean, it hurts too, actually. Yeah, you can break some bones, all right, because of the mechanical hit. But then the vest itself, it actually is getting hot too. But it depends on the material that it used, actually. Right now, they probably have some polymer, very high heat capacity, all this stuff. So it's going to be something like that. Okay, sounds good. So what is, okay, there's a question. Okay, the L is, okay, just to confirm over here, this is a latent heat. It's the energy that required to do the phase transition. Is the latent heat. Okay, let's go back to the table. There we go. Here we go. It's a latent heat right there. Okay. So on the first set over here, that's a latent heat of fusion. So when you transform from liquid to solid or solid to liquid. And then the second one, the second portion of this one is vaporization. So when you want to turn from liquid to gas. Okay, very good. All right. And once again, just to confirm that the reason we call them latent heats because there's no change in temperature. All right. Its phase transition happens at constant temperature at the transition temperature of each whatever material that you are talking about. Okay. All right. Very good. Any questions so far? All right. So if not, I think maybe this is a good place to stop because we are about to jump into the next slide. So, and then, oh, it's 45 minutes or so, 42. Okay. Sounds good. All right. So let's take a quick break right here. And let's take 10 and then we'll come back and then we move on to the next slide. It's handout number 2. All right, guys. See you in 10. All right, guys. All right, so let's welcome back to the business of thermodynamics. And this one, we jump right into the second handout. And today we are going to start talking about the work again. All right, and you probably remember work is just a force times the displacement in the direction of force. Yeah, but that is not going to be the case in thermodynamics subjects. All right, and we'll see how can we re-express that expression in thermodynamics. And if time is allowed, then we talk a little bit about the internal energy that we sort of like, talk briefly about what does it mean by total kinetic energy of the system. And then we're going to rename them and call them internal energy. All right. And if we master these two, we are right and ready to dive into first law of thermodynamics. All right. And then a lot of fun will start from there. Fun and confusion, I guess. That's what I'm thinking. All right. So let's start with this. It looks crazy, but it's not. All right. And it's sort of like, let's go through this one slowly first. It's going to look annoying at first. All right. But hopefully by the end of this lecture, it will feel natural to you guys. I hope. All right. So we will start at the system that is expandable because we need something, we need some action so we can trace and understand how thermodynamics work. So we're going to use gas as our study system, even though thermodynamics works in every forms of substance. All right, now we put a gas into a container and you have a movable piston. So that means you can move up or down, or the gas itself can expand and contract whatever it wants to. Okay. And now here comes the thing that we want to talk about. Somehow, if we have an external force acting on this gas, so let's say you compress the piston down, what happened to it? So first thing first, look back at the macroscopic level. I can actually ask you how much work is being done to the system. Don't forget, the system that we are talking about right now is gas. Let's stick with this. All right, stick with the system first. All right, so our system right now is being worked on. There is some external force. So see, so let me call this external. There are some external force. It's not by the system, of course. Somebody else, which is, it could be me, I'm pressing this gas down. So if I'm asking what is the work done by me or by the external force, you guys say about Ajahn, that's not hard because you have the force, you have the displacement. You can call this delta S vector. Then they are all in the same direction. So actually the work done by the external force is going to be the external force vector dot with the delta S vector. Cool. And that is done. And now we can put some coordinates into it. So if you say that let's use a normal coordinate direction, positive y is up. So what you have right now is, well, okay, is just the F times the dy. And because right now the dy is up, so actually what you have is down for the force. So this is the first expression is trying to explain to you. Okay, you guys with me? So I'm writing this in full. So what you have over here is the force is negative F times in the J, right? Negative J direction, so it's pressing down. The dy is always sticking up right there. So over here, you have this work done by the external force. No big deal. But then if I'm asking you in the opposite perspective, what happened to the system? The system will do some sort of like some reaction to it. So when you apply some external force to it, of course, they will have this equal and the same amount of the force acting backward. So the same amount. Okay, opposite directions, opposite objects, of course, I mean, it's going to be different objects. So what you have over here is you can think of the work done by the system is going to be just the opposite to the work done from the external force. You guys with me? So that's an easy portion of the things that you can add on top is right here. So always the work done by the system is going to be always opposite to the work done from the external force. But then we said, we don't want to deal with the force anymore because force is kind of like, yeah, it's inconvenience in like thermodynamic system. We would like to have something that's easy to account it for, easy to measure. We don't want to measure the force acting on the gas molecules. It's sort of like, you know, impossible to measure. So you can transform this into some parameters or variables that can be used in the macroscopic level. And one thing that we discussed this already. So instead of talking about the force for the gas, we talk about the pressure. And from the definition of the pressure, it is just a force acting on the surface perpendicularly. Cool. So that means I can re-express F in terms of the product between the pressure and the area. Does that make sense to you guys? So instead of using the force, I'm not going to use it anymore. I'm going to call it the pressure product with the area, cross-sectional area. But the good thing about this one is when you look at the cross-sectional area, and then you see that there is some movement over here. Let me overlay on the single figure over here. See that? So when you compress the piston, you see that the volume of the gas is changed due to the displacement dy and the cross-sectional area A. So that means that A dy can be expressed as the volume change. Why not? Okay, does that make sense to you? So that's why we can now talking about the work done by not talking about the force at all. We are going to only talk about the volume change. Every time that you see the volume change, there is a work done. But then it depends on your questions. You want to get the work done by the external force or you want to get the work done by the system. If you want to get the work done by the system, you just put the negative sign in the front. And that leaves you to this expression down here in green. In green, right here. Oh, in blue. Sorry. I have problem with the blue and green right here. There you go. That's it, guys. So the work done by the system in the thermodynamics system, at least you can use a macroscopic state variable, is the product between the pressure and the volume change. Done. Drop the pen. I mean, I'm just done. Drop the mic. Okay. That's what it is. So from now on, you can catch the work done by looking at the volume change. All right, that is a question. I got a feeling this will explain how compressor of the, oh yeah. It's like, oh, all right. Eventually, next week, you will learn how the air compressor works, how the, what else? It's like a refrigerator and everything. You're supposed to be able to understand everything. Yeah. All right, cool. So take this green equation to be the main equation for the work done calculation. The only thing that you need to catch is there any change in volume of the gas or not? It's that simple, seriously. Okay, let's look at this. To be able to explain the state of the gas, we once again, we lend the diagram from, I don't know, we lend them or they lend us. Okay, it's a PV diagram. All right, chemists use this, physicists use this, and I think biologists use this. It's a PV diagram. So it's a diagram that plots the state of the gas on the PV axis. The vertical one is the pressure, the horizontal one is the volume. All right, it's a PV diagram. The reason that this one is always good, because of course you guys remember PV equal to nRT, yeah? So PV is right here. Okay, and the good thing is, every time that you speak about a gas, it must be one state of a gas. So there must be a point on it that specify the state of the gas at that point. Cool? All right, now let's try this. If I start from point I, so you should be able to read from the scale, okay, that there will be some P, some pressure, P sub I, some volume, V sub I. That is your initial state of the gas. Eventually, I'm going to bring this gas to another state. Let's call that a final state. You can read it from here, what is going to be final pressure. You can read from here is what is going to be the final volume, yeah? But then the thing is, here comes a question. How? How can you bring the gas from I to F states? There are millions way. Actually, it's infinite, many variations that you can bring the system from I to F. Let's look at the three. The first one, you start from here. You guys focus on this. You start by compressing it down. You compress it. Yeah. The volume is reduced right here. And once you reach this point, you can call it M. I call it M. So you reach point M. Then from that point, you freeze the volume. So you're not changing the volume anymore. But then you raise the pressure of the system to stop at point F. Okay, you guys good? This is not a multiple choice, man. This is like 3 examples. Oh, come on, man. That's good. That's good.
Okay.
Okay. I'm just having fun with my sound effect here. Okay. Or I can do differently. I can start from point I with the constant volume. I just raise the pressure first. Don't ask me yet how, Ajahn. We will discuss that later, of course. And then once I reach point M here, and then I compress the gas at higher pressure, I can also reach my final point F. Or some of you might just come in, Ajahn, why you get going through so much trouble? I'm going to shoot from I to F directly using some weird process or whatever. There's so many ways that you can do this. Million ways. You can go as crazy as like, I'm going to go out there and come back here. You can go zigzag or whatever. I mean, whatever you want. But here comes the question. What is the work done going from I to F, guys? What is it? What is the work done from I to F? Choice C is the most easiest. No, this is not a choice. I mean, we have to be able to calculate work done on all of these process. All right. Okay. So the answer is this. You guys notice something? The definition of the work is PdV. When I say like this, it's a differential change, right? It's the P times a fractional change of the volume. I'm just going to call this dW as well. Yeah, remember, see it? I call it the D, yeah? If you want all of this work done, all you need to do is just, you're going to take dW and sum them up. PdV, 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 and then you just sum. That summation is just the integration. Okay, you guys with me now? All right, but then the P is the y-axis. The V is the x-axis. So actually this integral reflecting the y dx, does it look familiar to you?
Oh no.
Yes. So what is this? Of course, it's just the integration of some function, of course, some function y dx. And that is just the area under the curve. You guys with me now? So that's why there is some highlight, like a yellow shaded area, to explain the amount of work done in each case. That's it. So in conclusion, the work done by the system can be found from area under the curve in PV diagram. Yeah, it's not scary actually. This is not too bad. All right. I'll show you. It's quite easy to do. All right, but at least you guys know now. If you have a PV diagram on hand, the area under the curve will tell you the amount of work done. Yeah. Second question, guys. Here we go. Look at this. Now let's get a little bit more technical here. You're going from A to B. Let's say I have 3 processes or 3 methods bringing the system from A to B according to the path number 1, number 2, number 3. Let's calculate the work done on path number 1, guys. I really want to calculate it. How do we do? Well, Ajahn, it's just an area under the curve. You guys with me? Here we go. And come down here. So as you can see, the only portion that will give you some area under the curve is only the horizontal part of this path, number 1. And the amount of work done that you're going to get is just going to be area under the curve right here. I'm highlighting green right now. But from here, you can see, Ajahn, it's just a rectangular area. So yeah, if you can specify the pressure at point A, reading out from it, and there is the, volume at point A, and there's a volume at point B. So the area under the curve will be just the width times the length. And that's is going to be just PA, right? Times the width right here. But then, of course, we don't want to do geometry right here. What we want to do is, don't forget, is coming from the PDV, right? So let me write it in terms of an integral just to showcase what it is. So if I want to get the work done going from in the path number 1, it's going to be integral. PA is constant. dV, yes, going from point A to point B. All right, you guys got this notation over here. But P sub A is a constant. I can pull it out from the integral. So you are left with just the integral of the dV. The integral of the dV is just V. And take the limit. You're starting from V sub A. You end up at the V sub A. And that is going to be PA VB minus V sub A. You start to see what I'm trying to get to now? The direction is important again. You're going from A to B. Gas expands, guys. The volume is larger. And this mathematics is automatically give you positive change, see? Because the final volume is larger than the initial volume. So you can name this a delta V. So there's no doubt. If some of you still remember the high school thermodynamics, they say the work done by back in the day, they don't have calculus. If you don't have calculus built in, it's a P delta V. But that doesn't really work so well because this P delta V works only when you have a constant pressure. So that's why I want to stick with the integral expression of this. It seems to be better. All right, but anyway, the point is delta V, once again, stick with the final minus initial. So what I'm having right here is you're going from A to B is the expansion of the gas. Gas expands. So gas does work itself. So when the W is positive, work done by the system. You guys with me now? That is positive work done. Gas expands. If you want to calculate the work done going through path number 3, well, Ajahn, now this is not hard. If you want work done in the path number 3, what do? Just find area under the curve. But as you can see, the area under the curve is only this big right here. Right? So that means path number 3 will give you smaller work done by the gas. That's fine. Right? According to the PV diagram, that's what you can calculate. No problem. And if you want to go from A to B in the diagonal term, you just find the area under the curve. It's going to be a trapezoid area on and on. But the point is, Going from A to B, no matter which path you take, 1, 2, or 3, gas expands. And that is a positive work done right here. You guys with me now? Come back here. So now you should be able to answer my question here. If I'm asking you, going from I to F in the previous slide, is it a positive work or a negative work? See this? You're going lower in volume, all three of them. I mean, they must sharing the same thing. It must be negative work done. Very good.
Okay.
Oh, there's one positive. No, no, no. It must be negative work done. Because think about it, the gas eventually at the end is smaller in volume. So there must be somebody else outside like me compressing the gas down. So work is being done on the system. Okay, okay, okay. So this is a work done on the system. So every time you have the negative W, it means there's somebody else compressing the gas down. Okay, all right. What happened, Bojan? What happens here? Just this portion of the process is a vertical line in the PV diagram. Don't worry. If you are at a constant volume, there's no work done. See, that's how simple it is about accounting for the work done by or on the system is just looking at the change of the volume. Seriously, no volume change, no work done. That's it.
Okay.
Okay. Gas expands, positive work done.
Okay.
Gas contract, negative work done.
Okay.
Everything is revolved around the system. We talk about the system. W is the work done that we are focusing on the system. Cool. All right, it will get better. It will get better. All right, I'll when we talk more of the example and other stuff. Okay, let's practice. All right, do some calculation here for fun. An ideal gas undergoes a here we go, constant pressure expansion. Whoa, 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 whoa. This is not highlight. Sorry, constant pressure expansion. So if you see this in your head, imagine a vertical line. I'm sorry, a horizontal line, because it's a constant pressure expansion. So that means it must be fixed at one particular value of the pressure and is an expansion. So it must start from a lower V to a higher V. That's it. So in your head, you can have like a PV diagram mapping on that process going on. Okay. Its initial pressure is 1 atm. So that's a clue, given that is 1 atm right there. Its initial volume, initial and final volume are given to be 2 and 4. Very good. That's 2. And that is 4. The scale is bad, but I hope that's all right. Okay, that's a volume. There you go. Find the work done by the gas. See that? They want to know what is going on by the gas. Stick with the formula. Okay, I don't want to say stick with the formula. Stick with our understanding.
Okay.
Is an integral PdV now. Okay. And because this is an easy case, the pressure is constant, I can pull the pressure out. And all you have to do is net P delta V. So for the constant pressure process, the work done by the system is just P delta V. The pressure is given to be 1 atm. I can convert this to Pascal using some factor. All right, you can look it up, but it's approximately about 10,000 Pascal per atm. So that put it in the SI system of Pascal. And then the volume change is going to be final volume minus initial volume right there. And because it's an expansion, the final volume is 4, initial volume is 2. See, it's automatically positive. So it's going to be 10 to the 5th Pascal times 2 cubic meter. At the end, it's positive. What does it mean by positive? Is expansion by the gas, so the gas perform that work itself. Expands. If the question would like to ask you what is the work done on, that means if the question asks you about the work done on the system. All you need to do is just put a negative sign of the W system. That's it. That's how simple it is. Okay, guys? Cool. All right, good. And to emphasize again, what we are doing over here is equivalent to finding the area under the curve right here. It's a rectangular area that you have over here. It's the height times the width. Perfect.
Okay.
I hope. Next. All right. Any questions? I think this is good. All right. Try again, guys. So everyone try this. A 3 mole ideal gas undergoes a constant pressure expansion. All right. It's still pretty merciful to us right now. It's still constant pressure expansion. So imagine horizontal line in the PV diagram as usual. The initial and final temperatures are 300K and 400K respectively. Find the work done by the gas. Everyone do this. If we were to have quizzes, this is it. This is going to be the quiz of the day. All right, but we don't, so that's all right. Wait what? Don't wait. Just go for it, man. I'm still learning all this sound effect right here. All right, go for it. No, that's not good. That's not good. It's like time's up. Okay, 3 moles ideal gas undergoes constant pressure process expansion. Initial, final, but instead of giving you the volume, it gives you temperature. All right. I don't think we need to draw any PV diagram anymore. You guys got it? All right, stick with the definition, the work done. Oops, sorry. The work done, once again, I want to emphasize is the work done by the system is the integral P dV. All right. However, even though we would like to do a lot of integral, but we still don't need it because P is constant. All right. And now we just down with the PV final minus V initial, P delta V. Again, the constant pressure is good. No calculus needed actually. But then even though you don't have the information about the pressure and the volume, we don't care because you can use the PV equal to nRT. That's an ideal gas equation of states that works all the time. So you say it's a PV final minus PV initial, and that is going to be nRT final because N is fixed, R is just a constant, don't need to do anything, nRT initial. So you see how to combine the equation of state from the ideal gas law and the definition of work. Not too bad. N is known, R is actually, I can just wrap it up, is nR delta T if I want to. So it's N is 3 mole, R is just R. Let me leave it as R. You can look it up in the table every time. And the delta T is just, don't forget, final minus initial. So it's going to be 400 minus 300. See, at the end, you end up with a positive work done. So it's a positive 300 R joule. Done. And you're supposed to have a final answer to be positive because gas expands. Is an expansion of gas. Okay. Still pretty good. Okay.
Okay.
Keep going. All right, guys. Getting more complicated. Okay. Determine the work done on a fluid. Don't forget it works. It doesn't have to be gas. It can work at anything. However, if you are dealing with fluid, there will be no more PV equal to nRT. That's all. All right. But definition of work still work. All right. Determine the work done on. A fluid that expands from I to F as indicated in the figure. And B, how much work is performed on, okay, it's on the fluid if it is compressed from F back to I along the same path. All right, let's answer part A first, shall we? All right, everyone try. No, that's not it. That's not the sound effect for it. All right. Determine the work done on the fluid. Concept of the work done on is just the area under the curve. So actually you don't need to think too much because you already given a diagram over here. So the work done by, if you want, the work done by the system is going to be just the positive value of the area under, I mean, don't put the positive there. And I don't want you to think about that. It's just the area under the curve. All right. And then you can determine the sign by looking at the expansion, or is it an expansion or is it a contraction of the volume? Yeah. All right. So that's how it is. So first thing first, let's just calculate the area under the curve. That's what you need to do first. Let's assume that you know. It's just like rectangle here, a trapezoid right there, and another rectangle right there. All right, let's assume that is the number is A area. You get those areas to be A. So the work done by the system is supposed to be what, guys? From I to F. If the area is already calculated to be A, the work done by the system is supposed to be positive. Very good. And how much? How big is that? Positive. Anyone? Positive what? Yes, yes. Whatever you're thinking is correct. Yes. Just type it down. Whatever you're thinking is correct. I think you're thinking of it. It's the same. It's positive A. Yeah. If you found out what is the value of the area that you get from the area under the curve, going from I to F is an expansion. So that means the work done by the system is going to be positive of that value of the area under the curve. Got that?
Okay.
And the problem here asking the work done on, that means you are thinking of, hey, what is the work done by the external force? It's just going to be negative of that value. Cool? All right. And the value of the capital A is, I mean, your job to figure that out. Sorry, assume that it's easy to do. Come on, yes.
So if we compress the gas, why is the volume increasing?
Compressed.
Because external is with our system being pushed down, right, for external force.
Okay.
And why is the volume increasing then?
Okay, that's a good question. There is a negative sign there. So this means the external force is losing. The gas wins. You guys with me? So even though you're trying to press down the gas, but think of it when the gas is about to explode. And then you're holding the tank and the gas is expanding. You try to hold it down, but you're losing it. But the work done, right, by you is still trying to act on the gas, but the gas just wins. So in this particular case, coming from I to F, the gas is winning, but the work done by the force externally is going to be negative of that. Does that answer your question? Yes.
I'll think about it for a bit.
Okay. So when you say work done by the external force, it doesn't always means that the external force is need to compress the gas. Does that make sense? Because no matter what, okay, let me write it like this. So think of this as, okay, here we go. You have a universe. It sounds big, but that's what it means in thermodynamics. All right, that's a universe. That is your system right here. Okay. When the gas expands, okay, gas expands. This one, the gas perform work on the universe. the universe that your external stuff. So that means when gas expands, the work done by the external force or the work done by the universe is going to be negative of that. So it doesn't mean that the external stuff around the system doesn't do anything with the system. It still does. But at the time of the expansions, the external force is changing in the direction that's opposite to the force that's acting from the external agent. That's what it is. Okay, so it can happen on both sides. But if the gas is being compressed, so that means the work done by the external force is positive. So it's winning. So it's in the direction in favor of the direction of the external force. All right. But in our case, at this point, part A, the gas is expanding. So it's going against the external force. So that's why the external force is doing the negative work done. So that's sort of like, it's just two sides of the whole thing all the time. Okay, let's try part B. It might help. So once again, if you want to go backward, you want to go F back to I, but in exact same process over here. So in part B, the work done by the system is how much, guys? And this might answer your question. Going back from F to I, how much work is being done by the gas? Very good, very good, very good. Whatever you're thinking is good. Oh, you already got the answer. Okay, so let me talk about the system over here is going to be negative A. You guys with me? Because, I mean, no matter what, as long as you're following this trace or this path right here, you always talking about the magnitude of the work equal to A. But going from F to A, you get a compression. So the work done by the system is going to be negative. And then the work done by the external force, just like your friend just written there, is going to be negative of that. So it's a positive A. And this answers your questions that you talked about. This is when things go naturally. The external force doing the positive work and then compressing down the gas. Part B, that's the scenario that you might be more familiar with. Cool. Okay.
Okay.
I hope. All right. If this is good, keep going. All right. Last one before we move on to the next topics over here. And this is for you guys. And they could be the question in the exam, actually. This is about the exam level questions, even though the one before is pretty good as well, but it's more like this. A sample of ideal gas is expanded to twice its original volume of 1 cubic meter in a quasi-static process. All right, don't worry about this word just yet. We'll have a chance to sort of like dig deeper into what does it mean by quasi-static. But from the name implies something equilibrium, static-ish. It's quasi, so it's not perfect. All right, but anyway, the point is the process as shown in the PV diagram is some curve, and it's a parabolic curve, a alpha v square with a given alpha numbers. How much work is done on the expanding gas? All right, go for it, guys. 5 minutes. Let's do this. And submit your answer in the Google form. Just kidding. All right, no, we don't have quiz here. All right. All right, and I think after today's lecture, I think I will post, or maybe sometimes later, I will post the homework, or it's more like exercise for you guys to try, in the Google Classroom. All right, guys, try this one. You have a process from I to F. Now it's curved. All right, and we would like to calculate the work done by this gas. Oh, sorry, done on again. Oh, they love to talk about work done on. But don't worry, we can stick with our definition of W is a system. To me, I prefer talking about the system first, and then I just flip the sign at the end when we would like to talk about the work done on the system, which is the work done by the external force. All right. For those of you that still stuck, like don't know how to start, don't worry. Stick with the definition. Start with this. Okay. It's just a PDV and you sum them up. So they're going to be integral PDV. And next step should be quite obvious because now P has a relationship with the V given in the diagram. All right. What should be next? Good. Very good. Whatever you're doing is good. Okay, let's do it. Alpha V squared dV. You're starting from 1 cubic meter to 2 cubic meter. Very good. Alpha is constant. I can pull it out. V squared integral give you V cube over 3. You're going from 1 to 2. Good. And the alpha, you can substitute it in. All right. Don't worry about unit conversion. That's sort of like a little stuff that we can take care later. Yeah, that's an alpha. The volume. Okay, that is a third. Let me pull out the constant 1/3 out. And this is just going to be V final cubed. So that's going to be 2 cubed. Subtract 1 cubed right there. All right, guys, that's it. So it's going to be, what is that? 7/3 times 5. And it's in the unit of, it's not a joule yet. That's bad. So it's an ATM, right, per, all right, but we need some unit conversion, but I think you got the point right there. All right, so if I convert the ATM into Pascal, I think that would be the best. I should do that actually. All right, let's turn this into a Pascal. So multiply by roughly about this per ATM. All right, so I can turn that ATM into Pascal by multiply by 10 to the fifth. So at the end, I will get 7/3 times 5 times 10 to the fifth, and the answer will be in joule. All right, that is,
Okay.
I hope there's nothing left out here. I hope the number is correct. Yeah, is Pascal more popular? I don't think so. I think it's mixed. Like ATM is pretty good actually when you buying gas or maybe PSI. That's another one that used in car tires or in gas tank that people use in house or in hospital and everything. I think Pascal is not very popular per se. I mean, it's not like, I mean, you still use ATM for, I don't know, weather channel and everything. Talking about like low, high pressure and all this stuff. Okay, so it's mixed depending on the industry that you are in. But in our case, for SI system, we stick with Pascal. All right, guys, so it's good. So the key point to take home is work done. And as you can see, the mathematic will take care of the sign automatically because, see, your limit of integration will give you going from the initial point to the final point. Stick with the math. The final answer is positive. That means the work done over here is positive, of course, because you start from smaller volume to a larger volume at the end. So it's going to be an expansion by the gas. However, the problem asks you to figure out the work done on. So don't worry. So the work done on is just the work done by the external force or whatever stuff you just said. It's just the negative of what we just found out and you'll be done with. Okay, so I hope that the work done by or work done on won't get in your way, right? You should be able to answer either questions without any difficulties now. All right, stick to the math, but the math isn't sticking to my head. Okay, all right. All right, try to make the math a little bit stickier. All right. Okay, next. All right, here we come. I think what I'm trying to get you to understand is this. It might take me like 5-10 minutes to explain this slide. All right, but I hope this is the grand introduction to the thermodynamics. All right, and I am about to combine everything that we have learned into a single big law of thermodynamics right now using this scenario right here. Okay. All right. Start with this, guys. Slowly think about this. It takes time, but I think it will lead to something. You have a gas at initial temperature T sub I. Initial position of this piston is right here. And once again, you are in a tank with a movable piston. So that means that position can move up and down at the top of this container right here. So that means the gas can expand or contract, depends on what you want. But then here's the kicker. The bottom of this container attached to something we name energy reservoir. All right, we'll explain more a little bit later, but at least the name implies something huge that contain huge amount of energy. Does that make sense? When you say water reservoir, it means you have like a big dam or something, right? It's like, okay, holding tons of waters. That's water reservoir. Same thing with this. You have energy reservoir. It means you have a huge amount of energy waiting for you. But then here's the key. It's a at temperature T sub I, and that's make perfect sense. When you have a huge energy waiting for you, it should have pretty much constant temperature. You guys with me now? For example, you want the temperature of this room. Oh, this room may be a little bit too small. Talk about temperature of Bangkok, for example. It should have like some average value of maybe 30 degrees Celsius. And it's a huge energy reservoir. It means even though I'm turning on my air conditioner, I'm not going to be able to change the temperature of Bangkok area, right? That's way too big. That's what I'm saying. Okay. Or if I rub my hands, it's get warm locally on my hand, everything, right? It's get warm. But this heat that I'm generating right here is not going to be enough to change the temperature of the room. Does that make sense to you? So if you say the room, if it's a big room at some temperature, you can say that this is your reservoir of energy. You can steal some energy from the room, or you can throw some energy to the room. You won't change the temperature of the room. And I just changed the image of the room to be a little bit bigger, is like a Bangkok area. So that's for sure. Just by you're not going to be able to change the temperature of the Bangkok area. So that's what it means by energy reservoir. It's just a huge amount of energy, but because we already saw the connection between energy and temperature. So as long as you're not going to be able to change the amount of energy in the reservoir, you're not going to be able to change its temperature. Does that make sense? Like water reservoir. You're going to a reservoir, like a big dam, and you can steal some water from it, or you can dump some water into it. You're not going to change the height of the dam. I mean, not the water in the dam, for example. Yeah. So you can, bring some bucket of water, and then you just steal some water out from that dam. And nobody cares. The level of the water won't change. Okay, cool. So that's what it means by the gas make the contacts with the energy reservoir. When I say make contacts, we already learned about this. There will be some energy flow back and forth until it reaches some equilibrium point. So it's automatically saying that this gas is also at the same temperature. With me, guys? Eventually at equilibrium points. And because this contact does not disappear, so that's another way of saying that the gas in this system is at a single value of temperature all the time. And now gas expands, or we can just grab the piston and then just move it up. Doesn't matter, the effect stays the same. So what you have over here is gas expands up to the final position. So that means the volume of the gas is bigger. So gas does work. It's a positive work done by the gas. My question is, what happened to the gas? Maybe this question is like, what happened to the gas? I don't know what happened to it. The question I'm trying to ask is it possible for the gas to expand without doing anything at all? Temperature stay the same, and then if suddenly they're just like, okay, I feel like I want to be twice as big as the original size. Is it possible? You think? You have a balloon and they say, hey, I want to get the balloon to get bigger by itself. I don't think that is going to work. That's why what happened to it is there must be some heat flow into it. You guys with me now? You're probably not with me now because there's a weird example over here. When I say weird example, because this is a counterintuitive example. Every time that you talk about heat added to the system, your feeling go towards things gonna get hotter. But this is not the case. This system right here freeze the temperature. The temperature will not change. But it turns out you need something for the gas to expand. No matter what, you still need heat anyway. And there's a comment on here. There's no intermolecular force holding them together, right? That's not holding. It's just moving around. Gas just moving around. But then you have more volume of the gas to move around. However, the kinetic energy of the gas stays the same because you keep the temperature fixed. Isn't that cool? Something is going on right here. When you need to expand the gas twice as big, let's say it's twice as big, without changing its temperature, you need some energy, of course, right? Otherwise, then it won't be able to do the work. So to be able to do the work, you need some energy. And the flow in of the energy, we name it the energy transfer, right? It's in the form of the heat. So there is a heat flow into the system, but the heat here isn't being used to raise the temperature of the gas, but is being used to do the work.
Wow.
Isn't that cool? All right. If you still don't understand, don't worry. It will be better next time. Try again. Look on the right, guys. Almost the same scenario over here, but now we get rid of the movable piston and we assume that the container is now sealed, insulated. There's no connections to the external world, nothing, but the gas starting at the same initial condition, same temperature, same volume, same pressure, everything is exactly the same. And now it's being contained or being confined by a membrane. And let's say that the membrane just suddenly break. Bam, it just like expired. So the membrane just breaks. So the gas fill up the whole space. So from the look of it, the situation is going to be exactly the same from the perspective of the gas because we have the gas equation PV equals to nRT, right? So the gas starting from the initial volume, exactly the same temperature, exactly the same amount, same N, same pressure, same volume, same temperature. And then at the end, it's go twice as big, same temperature or not. What do you think? Well, Ajahn, in this case, there is no heat flowing in and out. Q is 0 because you are inside an insulated container. So no heat allowed to exchange. What about work done? Gas expands to twice as big. Does it perform any work done? The answer is no. But why, Ajahn? Because gas is twice as big. The reason is there's no work done because actual volume does not change. Can you see that? Even though inside the gas is twice as big. But that is inside. There's no way that you can feel the work done by the gas. What I'm saying is if I put my hands here, my ugly hand over here, I won't feel gas pushing my hands at all. Even though there's some crazy business going on inside this container, but you don't feel a thing. So that's why we say gas perform no work. When I say perform no work, I'm serious. For example, on the left, I can still use gas to lift some mass, for example. I might have like a rock. And then, hey, bring me up this rock. So see, on the left, gas can perform some work. But on the right, I can put a rock in here. Gas can do crazy stuff in there, but it doesn't help me raising up my rock. So that's why on the right, there's no work done. Okay. So on the right, no heat, no work. What do you think about what's going to happen to the temperature? Of course, the total energy of the system stays the same. So temperature stay fixed as well. So you start to see the business that we are trying to get to now. So the state variables is trying to tell you the state of the gas only. But to understand the process of the gas going from one to the other, you need to specify what kind of process that you are dealing with. The left-hand side process and the right-hand side process give you different amounts of W and the Q. Can you see things now? Okay. The W and the Q are different. On the left, gas perform works. There's some heat exchange going on. On the right, no work, no heat. But the gas can go from one to the other just like the same. So this emphasizes on the point that you can go from I to F. It depends on how you're going to go from initial point to the final point. You have to define the path. There's so many ways that you can get from one to the other. This is two out of those million, infinitely many ways of changing the system of the states of the gas. But here's the key. In these two cases, temperature are not changed. But we talk about the temperature. Temperature means energy. Total. So that means in these two cases, the energy of the system does not change.
Wow.
So the third stuff that we are talking about is the total energy of the system. We name it internal energy. Internal energy. And in this case, it does not change. Next time, these are the main roles that we are going to study. The work that we already introduced today, you guys know how to calculate it. Heat, we sort of, okay, is the energy transfer through the thermal contact and everything. Change of the internal energy, and then internal energy is just the total kinetic energy of the system, and it gives you the total amount of energy in the system. Is it going to change or not? Depends on the work and the heat. And the work and the heat depends on the path that you want to bring the system from I to F. These connections that try to link between these three variables and the process that you define the change will lead you to first law of thermodynamics. And that's what we're going to deal with it next time. Okay, sounds good? That is it for today, guys. Done.